I want to pull up the first handout for Module 2, right here on quadratic equations. So there's 3 main methods for solving a quadratic equation. And one is the quadratic formula. And the quadratic formula always works, but sometimes the equation will factor. And factoring can be a lot simpler than trying to calculate that formula. The formula, you have to be really careful about order of operations. And a lot of times people mess up with that. So you got to practice it. Now notice it says that this is how you find what we call zeros or roots of what would be a corresponding quadratic function, y equals ax squared plus bx plus c. So we've got 2 different animals here. We've got the quadratic equation where it's, you know, ax squared something times x squared plus something times x plus some number equals 0, right? So that's our quadratic equation. And this one we want to solve for x, right? But then here we've got, let me move this out of the way, we've got a quadratic function which gives a relationship between x and y that you can graph on the coordinate plane, and the graph is always going to be a parabola because it's really just a variation of the squaring function. And you can write y equals ax squared plus bx plus c. You can also write it as that same a, that same leading coefficient, times x minus h quantity squared plus k to see what the shifts are, right? That's a form where you've got a horizontal shift and a vertical shift and possibly a stretch or compression or a reflection. So I'll say can write as, and that is actually done by completing the square like we did for circles, right? To get a circle in center radius form, you complete the square in x and complete the square in y. So this is just completing the square in x. After you factor out, if there's a leading coefficient, you can't divide by it. You've got to actually just factor it out. So I'll show you that when we get to it. But first, we just want to solve these equations. So it says solve each equation using either the 0 factor property, completing the square, and then the square root property, or the quadratic formula. So let me do what I do sometimes, which is to add an extra page to show you what those 3 methods are. All right, so 3 methods for solving quadratic equations. One is where you factor and use the 0 product property or the 0 factor property. It's actually, yeah, okay. So factor and use the 0 factor property. Sometimes it's called the 0 product property. Actually, I think it's supposed to be product. I should change the this here should actually be 0 product property. Anyway, that property says that if you have a product that equals 0, then one of the factors has to be 0, right? There's no other way that 2 numbers can multiply to give you 0 without one of them actually being 0. I mean, think about it. 2 times 5, nope, not 0. 10 times 12, nope, not 0, right? It would have to be like something times 0 to give you 0. So if we factor the, that's supposed to be a 1 there. If you factor the quadratic, the trinomial, then, as long as you've got 0 on one side, that's the key. You gotta actually set equal to 0 first. Then factor and use the 0 product property. So, for example, suppose you've got x squared plus 5x minus 6 equals 0. So first thing you want to do is, since it's equal to 0 already, I could have started off, actually, let me do that. What if I started off and said equals 6, right? Then don't factor, right? Because it's not going to do you any good if you've got 6 on one side, right? There's no property of 6, right? There's a property of 0. So this is true if you want to use a quadratic formula also. You've got to set it equal to 0 first. So that's really important. Then you want to kind of unfoil, right? This is factoring. And you want to come up with, what two binomials multiply together to give you that. And so when the leading coefficient is 1 here, it's nice because it's just x and x. And then you just want to find two numbers here and here that multiply to give you a -6 and add to give you a +5. But you have to be really careful about the signs, right? Since this is negative, that means that the signs have to be different, right? This negative right here, maybe I should do this in red. When this sign is negative, that means that the signs have to be different. Right, for their product to be negative, because if the signs are the same, the product would be positive. Okay, so that gives you a plus and a minus. So now what you're looking for is two numbers really whose difference is 5. So it's not 2 and 3, is it? It's 6 and 1. And the 6 is going to have to be positive and the 1 is going to have to be negative so that the inside and outside combine to give you this middle term right here. Then you use the 0 product property and say, well, that means that x plus 6 equals 0 or x minus 1 equals 0. That's the only way that that product could be 0. So then you subtract 6 from both sides here and get x equal -6 as one of your solutions. And add 1 to both sides here to get x equal +1 as the other solution. It's always going to be the opposites, right? If you've got a +6, it's going to be x equals -6. And a -1, it's going to be x equal +1. Let me show you another example that's similar. What if it was x squared minus 5x plus 6 equals 0? How would that factor? X and x. Now, this is a positive, which means that the signs have to be the same. Notice up here, when your signs are different, you want two numbers whose difference is 5. Here the signs are the same, so we want two numbers whose sum is 5, or -5 actually. But we can just notice that they both have to be negative, right? Want two numbers whose sum is 5. So I always like to remember that if the signs are different, you want their difference to be the middle number. If the signs are the same, you want the sum to be the middle number. So here we do want 2 and 3, both negative, so that their product is positive. And then the inside and outside give you the -5. So now what? X minus 2 equals 0, or x minus 3 equals 0, gives you x equal +2 for one solution, x equal +3 for the other solution. And you do typically get 2 solutions for a second degree polynomial equation. Now, sometimes you'll get 1 or none, but usually you get 2 solutions for a second degree polynomial equation. Now, let me remind you what polynomials are. It's something times some power of x, and I'm going to call that a sub n, and then it's some other number, I'm going to call it a sub n minus 1, times the next power down, and it keeps on going so that you have these coefficients times some corresponding power of x to the first, or just x, and then it ends with just a constant. So you have this leading term that has the highest power of x, and it shows that it is of degree n. The number in front is called the leading coefficient, which has some things that it's going to tell us about the graph. The number at the end is just called the constant term. But basically, it's just a sum of powers of x with numbers in front of them. The one with the highest power, typically we write first. That gives you the degree. And then if there's a constant term, that kind of goes last. And just we typically put them in descending order of power. So a constant function is actually a 0 degree polynomial. Constant function y equals a. Actually, I like to use b. Is, remember, a horizontal line that hits the y-axis at b. That's its y-intercept. That's why I wanted to use b. So that's 0th degree. 0th degree. Let me put that in up here a little bit. Oops. 0th degree. So that's a polynomial function. A linear function, y equals mx plus b, is a first degree polynomial function. Y equals mx plus b. Right? It's like it's just got these last 2 terms. Right? The 0, the constant function just has the constant term. The linear function just has the power of the multiple of x and the constant. So that's first degree. And then quadratics are second degree. Quadratic function has the last 3 terms, right? Y equals ax squared plus bx plus c. This has these last 3 terms. And we're going to look at some higher degree polynomials as well. All right, I need another page. Let's do it after page 1. Come on, change to after. There we go. Okay, so another way of solving, completing the square. back to, ways of solving quadratic equations. Completing the square. So this is best if you have a leading coefficient of 1 and an even middle term, even middle coefficient, and it doesn't factor. Something like that, right? That doesn't factor because you would need just 1 and 1, and that doesn't give you 6, right? So again, it's nice if you have a leading coefficient equal to 1 and an even coefficient here, and it doesn't factor. Here's what you do. You first move the constant term over, kind of like we did with circles, remember? We set up a template where you just have the x terms plus blank, move the constant over to the other side. In other words, subtract 1 from both sides and put a plus blank over here. So remember, you've got this kind of template for completing the square. And then what do you add? You take half of that. That's why it's nice that it's even. And then you square it. Half of it, of course, would be 3. Squared would be 9. And you add that to both sides. Because then what that does is allow you to factor that trinomial as x plus 3 times x plus 3, or x plus 3 quantity squared. And then you just combine the numbers on the other side, in this case to get 8. So then we use what's called the square root property. Which says if you have something squared equal to a number, then the thing without being squared is plus or minus the square root of that number. Okay, so here we have something squared equal to a number. So that something, x plus 3, is plus or minus the square root of that number. Then what you do is simplify the radical if you can. 8 does have a perfect square factor of 4, right? 8 is 4 times 2, so we can take the square root of 4 out of the radical and get 2 root 2. And then subtract 3 from both sides to get x by itself. We usually just write the -3 in front of the plus or minus. Okay, so again, it's two solutions, right? -3 plus 2 root 2 and -3 minus 2 root 2. In fact, those are symmetric around the number -3. If you look at, 2 root 2, if I approximate that on my calculator, that one's dead. Here we go. 2 times the square root of 2 is approximately 2.8. So that means that these solutions are approximately -0.2 and -5.8. Right? If you add or subtract 2.8 to and from -3, look at a number line here. Here's 0, 1, 2, 3. Here's -3. If I add 2.8, I'm here at -0.2. If I subtract 2.8 from -3, I'm right about there. See how they're symmetric around -3? The vertex of the corresponding function would be would have x coordinate -3. I'll write that here. That's going to be the x coordinate of the vertex. Of the parabola, the graph. Well, of the graph of what? Of the graph of the corresponding function. Of the graph of y equals, what was the original equation? X squared plus 6x plus 1. Right? That would be the corresponding quadratic function for this quadratic equation. What these solutions actually give are the x-intercepts of the graph. These would be the exact, these would be the approximate x-intercepts of the graph. So that's what is meant by this idea of finding the zeros. The zeros are going to give you the x-intercepts, unless they come out to be imaginary. And that, of course, can happen if right here, this 8 that I took the square root of was negative, then I would end up with imaginary solutions. So if the solutions are imaginary, that means that the graph doesn't have any x-intercepts. It's a parabola, remember? So it could be entirely above the x-axis or entirely below and upside down. So if the solutions are imaginary, actually they're called complex, where they're in the form a plus or minus bi, then there are no x-intercepts. So we're solving these quadratic equations, getting ready to analyze the graph of the quadratic function. So there's that relationship there. All right, and then there's the quadratic formula, which I'll go ahead and show you on number 1 here. Although number 1 really might even factor. Yeah, I'll show you the quadratic formula when it looks like it is a good idea. This one actually we could use any method. And I don't have room right there, so let me go insert another piece of paper. Oh, we got answers. Definitely want to insert a piece of paper before the answers. Insert. After page 3, yes. Okay, number 1. Number 1 is x squared minus 4x equals 60. So method 1 would be if it factors. Let's look and see if this thing factors. Remember, you have to set it equal to 0 first. Does it factor? I tend to think factoring is the easiest if you can get it to factor. And again, this being having a leading coefficient of 1 means it's typically easier to factor. If it does factor, you want to find 2 numbers whose product is negative 60. So that means the signs would have to be different. So the 2 numbers have to have a difference of 4. What goes into 60? How about 6 times 10? Those have a difference of 4. Yes. And which one's which? Which one goes where? Well, we want a negative 4, so we want the bigger number to be negative. See that? So 6 times negative 10 gives you that negative 60. And then on the inside and the outside, you get a 6x minus 10x. That gives you the negative 4x. So that works. So then you set each factor equal to 0, and you're going to get the opposites, right? X equals negative 6, and x equals positive 10. Now, this one would work well for completing the square, too. You could say, all right, well, I've already got that constant on the other side. Let me just put in a plus blank and a plus blank. Half of negative 4 is negative 2. Squared is positive 4, so I can add positive 4 to both sides. And then this trinomial factors x minus 2 times itself equals 64. So then I can take plus or minus the square root of both sides. Square root of 64 is 8. And then adding 2 to both sides gives me 2 plus 8 or 2 minus 8, which is positive 10 or negative 6. What do you know? Always make sure you split up to the two answers when you can simplify it. Now, the quadratic formula also always works. It says if ax squared plus bx plus c equals 0, so you have to have it in this form, then x is going to be the opposite of b plus or minus big square root b squared minus 4ac all over 2a. And really that has originates from completing the square. Have you ever seen a proof of the quadratic formula? You should see one. Once in your lifetime, you should see a proof of the quadratic formula. I'm going to show it to you. Proof. So here, it's kind of complicated because of the a. You've got ax squared plus bx plus c equals 0. So what you have to do is you have to divide both sides by a. Remember with circles, you can't complete the square if there's a leading coefficient there. So dividing everything by a gives you x squared plus b over a times x plus c over a, and then 0 divided by a is still 0. So then you set up your template for completing the square. So you move the c over a, that's the constant, you move that over, and you go plus blank, plus blank. What goes in the blank is half of b over a squared. So that's b squared over 4a squared. B squared over 4a squared. So then this factors as x plus b over 2a, because it's always that number, squared. And then over here, you need a common denominator. So you have to multiply this by 4a over 4a. So you get a negative 4ac plus b squared all over 4a squared. So then you can take the square root of both sides, plus or minus, to get x plus b over 2a equals plus or minus, and here you can kind of see the quadratic formula emerging. This is b squared minus 4ac if I turn that around, and the square root of 4a squared is 2a. And then if I subtract b over 2a from both sides, that is essentially the quadratic formula right there. But what we usually do is we put them together, right? We put negative b plus or minus the big square root all over 4a, or 2a. But sometimes I think it's too bad that we split it, that we put it together, because a lot of times people don't realize that, you know, the negative b is over 2a and the radical is over 2a. And they try to like reduce part of it, but not the other. So you really have to remember that both of them are over 2a. So it might be better to remember your quadratic formula in that form, as opposed to the more common form. Or just remember that, you know, 2a is under both parts. All right, so let's do number 2 up here with the quadratic formula. So what you do is you identify a, b, and c. A is 1 for this one, b is 6, c is 16. This one actually looks like it might factor, but I don't think it does, because you'd have to have x and x. You'd have to have different signs. So you'd have to find two numbers that multiply to give you 16 whose difference is 6. Oh yeah, there are 8 and 2. Okay, never mind. I'm not going to use a quadratic formula on this one. 8 and 2. With the 8 positive, that works, doesn't it? 8x minus 2x. All right, so x is negative 8 or positive 2. So you see how using factoring can be a lot quicker. And in fact, the 3, 4, 5, and 6 are all not good candidates for the quadratic formula because each of them is missing a term. Number 3 doesn't have a constant term. When that's the case, you can factor out x. Factor out x. And then setting each factor equal to 0 gives you your two solutions. Numbers 4, 5, and 6, these are all missing an x term, right? No x term. So these, you want to just use the square root property. I'll say the plus or minus square root property. Number 4, x squared is negative 36. So x is plus or minus, don't forget that, the square root of negative 36. What is the square root of negative 36? It's imaginary, because I'm going to turn off that chime because people are coming and going and it's bugging me. Play sound. There we go. All right, so the square root of 36 is 6, and then the square root of negative 1, by definition, is the imaginary unit I. Remember? Square root of negative 1 is I. That's by definition the imaginary unit. So you can kind of think of negative 36 as negative 1 times 36. Take the square root of 36 and then tack on your imaginary unit for the square root of negative 36. This one, by the way, corresponds to the function y equals x squared plus 36. What does the graph of that function look like? Right? If I were to set this equal to 0, I would get x squared plus 36 equals 0, right? So this is the corresponding function. What's the graph look like? Well, it's just the squaring function shifted up 36, right? So it'd be like way up here. It doesn't have any x-intercepts. because it's way up there where it, its vertex is up 36 units. This one, I'm getting these kind of squished together here, but this one right here, the function would be y equals x squared minus 32. That one is down here, shifted down 32. So that one does have a couple of x-intercepts. X squared equals 32. X is plus or minus the square root of 32, which doesn't come out even, but again, you could pull out 16 and take the square root of 16. Square root of 16 is 4. So 4 root 2, which is approximately square root of 32 is approximately 5.656, 5.7, plus or minus. So that's where it hits the x-axis. And then number 6, 3x squared equals 81. So x squared is 27. X is plus or minus the square root of 27. You could pull out the square root of 9. And there would be a 3 factor left inside. So those would be the x-intercepts of that function of y equals 3x squared minus 81. So again, there's this relationship between solving the quadratic equation and looking at the x-intercepts of the corresponding function. Because if you think about it, the equation just has a 0 where the y would be, right? The corresponding function is just having a y equal to it instead of 0 equal to it. And when y is 0, you're on the x-axis. All along the x-axis, y is 0. All right. Number 7. This one, put a little box around this. Number 7, I don't think that factors. What do you think? I think that there are no two numbers that multiply to give you a -3 that then add, or actually their difference, right? Because the signs are different. Difference would be 5. Can't be, because the only factors of 3 are 3 and 1. So you can't get 5x from 3 and 1. So this is a good quadratic formula. So A is 1, B is 5, C is -3. So what I would recommend that you do is write down the quadratic formula each time you use it. So eventually it's, in your head, all over 2a or each piece over 2a. The opposite of B is -5. You can put that in, right? So if B is negative, the opposite of B is going to be positive, right? So watch that. Plus or minus, make sure your square root is nice and big. B squared, you can usually do that in your head. B squared, 5 squared will be 25. But then 4 times A times C, be really careful with that because you don't want to make a sign error. So 4 times A is 1, C is -3. Make this a little bit bigger. Ooh, a lot bigger. And then all over, and then 2 times A in this case is just 2 because A is 1. Okay, now what you want to do is the what we call the discriminant, what's under the radical. Be really careful. That's where the order of operations is important. You've got to do the multiplication here first. Multiply before subtracting. A lot of people want to do 25 minus 4 first, but you can't. So negative 4 times 1 times negative 3 actually gives you a plus 12, doesn't it? You take that minus, put it with the 4. So 25 plus 12, maybe I'll go back to pink. 25 plus 12 is 37. I think 37 is prime. Definitely no perfect squares in there. So that means that that's, you know, as simple as it gets, except for you could possibly write them separately, right? There's a one with a plus and one with a minus. I'm not sure if XYZ wants you to separate them or not, but it might. And then if you wanted to approximate them, if they ask you to, you know, give them as approximations, you would do the negative 5 plus root 37, hit enter, and then divide by 2. That would give you approximately 0.541. And then negative 5 minus root 37, hit enter, and then divide by 2 to make sure that you do, you know, the whole numerator. You've got to, you know, think of that in parentheses. And that gives you negative 5.541, which you can also see are, you know, kind of symmetric around negative 5. Is that right? No, they're symmetric around negative 5 halves. Negative 2.5, yep. But there's a symmetry there. Actually, we'll see when we look at quadratic functions that the x-coordinate of the vertex of a parabola is always negative b over 2a. It's always this first part of the quadratic formula. So I'll give you that as what we call a vertex formula. We call it H. All right, this is getting a little crowded. I might have to get another page. So number 8. I can do number 8 here, and we'll just hold off on number 9. I'll do number 9 on another page. Number 8. This one first. Let's get that negative 1 over on the other side. So add 1 to both sides, right? You can think of it as transposing. When you bring a number across the equals, it changes sign. But it's basically adding the opposite to both sides. So that one doesn't look factorable to me, and it'd be kind of complicated because of that 2 there. You'd have to do some trial and error. So let's go right to the quadratic formula. Negative b, I've got it right here, so I'm not going to write it down again. It's right here. Negative b would be a positive 6 for this one, right? Plus or minus, big square root. B squared is 36. That b squared is always positive. Minus 4 times a times c. Here I always put parentheses in because I want to be careful about signs, but it looks like they're all positive here. So again, you got to do that multiplication first. This is all over 2a. Since a is 2, 2a is 4. Okay, 4 times 2 times 1 is 8. So we've got 36 minus 8. under the radical, which is 28, isn't it? Here's where you got to be careful about reducing, because 6 over 4 reduces, but the square root of 28 is over 4 also. So what I like to do is actually split it up. 6 is over 4, but root 28 is over 4. And root 28 does simplify because 28 is 4 times 7. So you can take the square root of 4 out to root 7. That's over 4 also. So reducing this gives you 3 halves plus or minus root 7 over 2. Or you could keep it together as 3 plus or minus, or put it back together as 3 plus or minus root 7 all over 2. And again, you could write them as plus and minus, right? 3 halves plus root 7 over 2, 3 halves minus root 7 over 2. And then if I had room, I could also approximate them. Okay, so actually I think I've got room down here to do number 9. X squared plus 4x plus 7 equals 0. So that doesn't factor because, you know, there's no two numbers multiply to give you 7 and add to give you 4. But this is a good one for completing the square because that 4 is even. And I can subtract 7 from both sides and put in plus blank plus blank. Half of 4 is 2, squared is 4. Add 4 to both sides. Then x squared plus 4x plus 4 factors as x plus 2 times itself. And you end up with a -3 on the right-hand side of the equation. Using the square root property, x plus 2 is plus or minus the square root of -3, which is plus or minus root 3i. You could write the I in front of the radical or after. Just make sure the I is not under the radical. So x is -2 plus or minus root 3i. Complex. So the function y equals x squared plus 4x plus 7 has no x-intercepts. Must be entirely above, probably above the x-axis because everything's positive. Maybe I should call it f of x instead of y. Right? Same thing, but looks more like a function when you call it f of x. All right, one more. Number 10. Let's see. If we set this equal to 0, 4x squared plus 2x plus 1 equals 0. Bringing those terms over, making them positive. I don't think that'll factor. You know, factoring something like this, you'd have to use trial and error. Everything would have to be positive. So nope, that's not going to work. 2x plus 1 and 2x plus 1, that's not going to work because that would give 4x in the middle. This one gives 5x in the middle. So yeah, it doesn't factor. So quadratic formula, we've got a equals 4, b equals 2, c equals 1. Here's our quadratic formula. So x equals -2 plus or minus big square root 2 squared is 4 minus 4 times a times c. A little crowded there. Let me make that a little bigger. All over 2 times a is going to be 8. So let me go over here. X equals -2 plus or minus. 4 times 4 is 16. 4 minus 16 is what we have under the radical, yeah? And again, you might want to keep in mind that both of these are over 8. 4 minus 16 is -12, which is not a perfect square, but 4 times 3, you can take the square root of 4 out, and of course the square root of the negative is I. -2 over 8 is -1 over 4. And then we've got 2I root 3 over 8. So -1/4 plus or minus I root 3 over 4, or we could write it as root 3 over 4I. You could also write it all over 4, but complex numbers, it's a lot of times nice to split the real and the imaginary part separate. Any questions on any of those? So you can use whichever of the 3 methods you want. The ones, that are missing a term, like if they're missing an x term, solve for x squared and use the square root property. If it's missing a constant term, factor out an x. Otherwise, set it equal to 0, see if you can factor, or you can use the quadratic formula. It's totally up to you. Let's see. Yeah. What else? Got the answers here. And now we're going to look at quadratic functions. So y equals, or f of x equals, we want to convert to what we sometimes call vertex form, where we can see the vertex in terms of shifts. And then we can see what's called the axis of symmetry. X equals the x coordinate of the vertex is going to be the line that cuts the parabola exactly in half. When the leading coefficient is positive, it opens upward, right? Greater than 0 means positive. When the leading coefficient is negative, it opens downward. So here's a pretty tough example, really, but it's good to have one that you can follow. If you have a leading coefficient of 2, or any leading coefficient, you first have to factor that out. So this is where completing the square is tough, but I was going to say it's the only way. It's really not the only way. The other way is to use the vertex formula. So this is just, again, just one option. And then I'll show you the other option. So completing the square, you factor out the 2 from the x terms. Notice factoring out a 2 from the 2x squared leaves you with x squared. Factoring a 2 out of 5x, well, it doesn't factor out evenly, so you're left with 5/2 x. See, if you were to go back and distribute that 2, you'd end up with the 2x squared plus 5x again, wouldn't you? So you just factor that out of the x terms. Keep the plus 7 just as it is. And then inside parentheses, with the x terms, you complete the square, where you take half of that coefficient, which is 5/4 squared. All right, 5/4 squared is going to be 25/16 actually, right? That you add inside parentheses and subtract outside parentheses. But notice this 2 has to be there as well because this 2 is out here. So it can get pretty nasty with fractions when you have to factor out. But then this factors, and you combine these, and you end up with a lovely function in vertex form. This is x plus 5/4 quantity squared plus 31/8. Nice, huh? So the other way is to use these formulas where h is always negative b over 2a, and then k is what you get when you plug that into the function, right? Because it's the y coordinate. So in this case, negative b over 2a was negative 5 over 2 times 2. That gives you the negative 5/4. Or you could put it in decimal form if it's exact. And then you can plug that in. And this, of course, you can just do with your calculator. Let's see if I can pull my calculator up here. Oh, you know what? I have to change my sharing because I'm not sharing the whole screen. Well, I'll tell you what, let me stop sharing with this one. I'm just gonna pull it from one screen to another so that I can then pull it back and use the whole screen. And I want to hide those and make that smaller. Oh, that didn't work. There we go. Okay, so clear. Negative b over 2a. So you just look at your function. Here's a, here's b, here's c. So negative b would be 5 divided by, and then in parentheses, 2 times a gives you the x coordinate of the vertex. And remember, to get it in fraction form, you can just hit your math button and then enter twice, math frac, to get it in fraction form. So then to plug it into the function, you just go 2 times that previous answer. Second negative is the previous answer squared plus 5. Oops. You only want one plus. 5 times the previous answer plus 7. See what I did there? So you calculate your x coordinate by negative b over 2a, and then plug that previous answer into the function. So you're just doing second negative for a and s for x. And there's your y coordinate of the vertex. And because you had changed the x coordinate to fraction form, it knows that that's the form you want the y coordinate in. So that's kind of cool. Much better than completing the square. Although completing the square can be easy. Again, if you have a leading coefficient of 1 and an even coefficient of x, like this one right here. You can just go y equals x squared plus 6x plus blank, move the 8 over. You don't really have another side to use. I mean, you could, but it's easier to just move that 8 over and then go minus blank, right? When you're on the same side of an equation, adding something and subtracting it is a way of kind of keeping it the same, right? So what do we add? We take half of 6 squared. So I'm adding 9 and subtracting 9 on the same side, because then this trinomial factors x plus 3 times x plus 3, and these two numbers here combine to give you minus 17, which is going to be the vertical shift or the y-coordinate of the vertex. So the vertex, remember, is the opposite. You have a kind of an opposite horizontal shift, and then minus 17 for the vertical shift. The axis of symmetry is always going to be x equals the x-coordinate of the vertex. Now, the x-intercepts, remember, that's what you get if you solve the equation, the related equation. So we want to solve that. And does this factor have to be two different signs to get a negative 8? Factors of 8 whose difference is 6? I don't think so. So then, again, you've got the two other options, completing the square or quadratic formula. But look, we already completed the square right here. So what if we set that equal to 0? That would be exactly the same as setting the original expression, the original way it was given. And now we can add 17 to both sides and see that, yeah, the reason it doesn't factor is because you get some irrational solutions. Plus or minus the square root of both sides, and then subtract 3 from both sides to give you negative 3 plus or minus root 17. So the x-intercepts are actually the points, negative 3 plus root 17, comma 0, because y is 0, or negative 3 minus root 17, comma 0. Of course, if you wanted to approximate those, you can get out your handy-dandy calculator and type it in. Plus root 17. So approximately 1.1230, and then the one with the minus, I'm going to do a second enter, which retypes what you just typed in and change that to a minus. Negative 7.123 are the approximate one. Right, that's what you'd want if you had to actually plot them on a coordinate plane. Now the y-intercept is easy because the y-intercept is where you plug in 0 for x. So that's going to give you the constant term right there. All right, because the plugging in 0 for x makes those first terms go away. So that's going to be negative 8 for y and 0 for x. And then which way does it open? This one has a positive leading coefficient, so it opens up, right? Because it's got a leading coefficient of positive 1. Positive coefficient of x squared. So then we could actually graph that without too much trouble. I wish I could pull up. I don't think it'll let me. I want graph paper. See what it says. Probably wants me to pay for it. Yep. I thought so. Never mind. I have some that I'll use after we finish these two. I'll show you. So we'll graph it later. Number 2, the vertex of this one. Again, it's easy to complete the square because the leading coefficient is 1 and the coefficient of x is even. That allows you to go plus blank, then write the constant, and then minus blank. So that's what the template looks like for completing the square for a quadratic function. Plus blank and minus blank. Just leave the constant there, either in between or on the end. In fact, that might even be nicer. If we just go plus blank, minus blank, and then the minus 4. What goes in the blank? Half of -2 is -1, squared is 1. That goes in this blank also. So we're adding 1 and subtracting 1, which is 0. So we're not changing it. But then we group. We say, okay, we got a trinomial here now that factors x minus 1 times itself. And we've got two numbers that just combine to give you -5. And there's your vertex form. So the vertex is the opposite of this number together with this number. So +1, -5 is your vertex. The axis of symmetry is x equals 1. Then the x-intercepts, again, since we completed square, we can set that equal to 0 and use the square root property because they're not rational. X minus 1 is plus or minus the square root of 5. So +1 plus or minus root 5. And because it's they're x-intercepts, there's 2 of them, one with the plus, one with the minus, and the y-coordinate is 0. Right? Because it's essentially, we put in 0 for y. We've got 1 plus root 5 and 1 minus root 5. And those would be approximately 1 plus root 5, 3.236, and second enter with a minus, oops, -1.236. The y-intercept again is nice and easy. G of 0 is -4. So that's 0, -4. And the opening direction for this one is also upward because the leading coefficient is positive. All right, number 3. This one is not easy to complete the square because this leading coefficient is 2 and you'd have to factor that out. The good news is that this would still be even. So you'd have x squared minus 4x, and then you could add, and then you've got +9, and then you'd subtract 2 times whatever you added. So it could be done, but the other way to do it is to use h equals -b over 2a. which would be -8, so +8 over 2 times 2. So I'm going to use my calculator. 8 divided by 4, right? I can do 2 times 2 in my head. So that's 2. And then I can plug that into the function. 2 times 2 squared minus 8 times 2 plus 9. With a positive number, it's kind of easy. So K is 1. So that's your vertex, 2, 1. So completing the square is kind of yucky. All right, so now for the axis of symmetry, that's always x equals h. Now for the x-intercepts, I'm going to use the quadratic formula because I want to set this equation equal to 0. Sorry, the quadratic expression equal to 0, setting, plugging in y, plugging in 0 for y. So let's use the quadratic formula. Negative b would be a +8 plus or minus. B squared is 64 minus 2 times a times c all over 2a. Hang on a second. All right. Then multiply before you subtract. 2 times 2 times 9 is 4 times 9 or 36. Of course, we could do, you can do that here. 64 minus 2 times 2 times 9. It does know the correct order of operations. Square root of 28 all over 4. And then 8 over 4 is 2. But then square root of 28, again, is square root of 4, or 2 times the square root of 7 all over 4. So that reduces to 2 plus or minus √7 over 2. Like so. I've got some stuff in the way here. I've got to make this smaller or something. Hang on. There we go. It still doesn't want to cooperate. Here we go. So yeah, 2 plus or minus √7 over 2. Move that little 2 over a little bit. Would be fine. So 2 plus √7 over 2 comma 0 and 2 minus √7 over 2. You can see those are in fact symmetric around that axis of symmetry. √7 over 2 is kind of added and subtracted to and from 2. The y-intercept is going to be what you get when you plug in 0 for x, and that's going to give you that constant of 9, and this one is also opening upward. All right, so now I'm going to get out some graph paper and put these on a graph. So I'm going to switch to my document camera. All right, let's see. First, I need to turn on the software for my document camera. And then share screen. Yes. Come on. Doesn't appear to be working. Let me try it again. Let's go with the other monitor. There we go. Okay. So number, I gotta get my other thing back here so I can see it. Here, there's my tablet. So I'll be looking at my tablet while I do it on paper here. Hopefully you've got it written down too. So number 1 was y equals x squared plus 6x minus 8. So this one, we had a vertex at -3, -17. So 1, 2, 3, there's -3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Right there is my vertex. And the axis of symmetry again is this line. Goes right through that vertex. That's what's going to cut the parabola in half. The x-intercepts were approximately 1 point something, 1.123, and -7 point something, 4, 5, 6, 7. -7.123, right? Basically -3 plus or minus the square root of 17, right? So symmetric around that axis. The y-intercept was 0, -8, 2, 4, 6, 8, right there. One thing we also get from that y-intercept and the axis of symmetry is there's another point over here that is the mirror image of that y-intercept around the axis, right? This is 3 units from the axis in this direction, so there's going to be a point 3 units from the axis in the other direction. So then you can draw in your parabola through those points. Of course, so in XYZ, you'll have some parabola tool that you can use. It's a little bit easier. But that's that one. Number 2, g of x is x squared minus 2x minus 4. Let's see. Draw my axes. The vertex is 1, -5. So over 1, down 1, 2, 3, 4, 5. Right there. The axis of symmetry is the line x equals 1. Right? That's the line that has x coordinate 1 on all the points. And then the x-intercepts are 1 plus and minus √5, which is approximately 3.2, right about there, and -1.2, right about there. Symmetric around that axis. The y-intercept was 0, -4. So again, we've got another point symmetric across from that, and then we can draw it in. And then number 3, y equals 2x squared minus 8x plus 9. In fact, let me also write the vertex form of the equation because they're both equivalent, right? So this one was x plus 3 quantity squared minus 17. This one, g of x, is also x minus 1 quantity squared minus 5, because they're going to want that probably as well, the alternate version of the function. And then this one we have to be a little bit clever about because we didn't complete the square on this one. So we just have to remember that it's going to still have this 2 out in front. And then it's going to be x minus the x coordinate of the vertex, which was 2, quantity squared, plus the y coordinate of the vertex, which was 1. All right, so this one had a vertex at the point 2, 1, over 2, up 1. So it had an axis of symmetry right here. X-intercepts were symmetric around that 2 plus root 7 over 2 and 2 minus root 7 over 2, which I did not calculate. Let's see. 2 plus the square root of 7, and it was just the root 7 that's over 2, not the whole thing. So 3.3 approximately. That doesn't make sense. Something's wrong here because if the vertex is at 2, 1 and it opens upward, we can't have x-intercepts down here, can we? What happened? We used the quadratic formula. B squared was 64. Well, it definitely came out real. Vertex was positive 2. We plugged in 2 to the equation. 2 times 2 squared minus 8 times 2 plus 9. And we got 1. Something is wrong. Did anybody catch it? Let me look at the chat here. What did we do wrong in number 3? We. See what I'm saying? If you have a vertex here and it opens upward, it can't have any x-intercepts. So we should have gotten imaginary solutions for x. Negative b plus or minus b squared minus 4ac. Oh man, I found it. Look here, let me share this. Look at this mistake I made. That's terrible. It's right here. Right here. That's supposed to be a 4, not a 2. Oh, for crying out loud. That should be a 4. 4ac. Oh, you guys need to be more alert than that. Okay, so 4ac, 8 times 9 is 72. Yeah. So 64 minus 72. Here, I'll do it here. 64 minus 4 times 2 times 9 is what it should have been. Negative 8. Yeah. So that is, let me clear this, because actually we don't have any x-intercepts when this happens. When you get a negative discriminant, a negative under that radical, let's see, that is -8 is 4 times 2. Well, -4 times 2, but the negative is going to come out as I. And then we got a 2 root 2 over 4. So that's going to be 2 plus or minus root 2 over 2I. And because that's imaginary, there are no x-intercepts. Sometimes we put DNE, does not exist. Okay, that's better. Sorry about that. I see it's good to graph something and make sure that everything works out. So back to this one. All right, so yeah, no x-intercepts because we have a y-intercept at 0, 9, 2, 3, 4, 5, 6, 7, 8, 9, which gives us a mirror image of that over here. So it's opening upward away from the x-axis. All right, any questions on that? So let's take a little break, and then we're going to look at solving some other kinds of equations that are similar to quadratics, but are not. They're what we call in quadratic form. But let's take a 5 or 10 minute break. I'm going to go ahead and pause the recording. Okay, so now we're looking at equations in quadratic form. You can see my little picture at the top here. It's where you've got some number A times some box, something in something squared, plus some number B times something plus C equals 0. So it's looks like a quadratic equation, but that box doesn't have to be just X. So you can see these equations are kind of that form where, especially number 2 here, you can see that you've got this x squared, and then x to the 4th is the square of that. That's kind of the idea, is that you've got some middle term, like here, you've got 2x minus 1 to the 1/3 power. If you square that, that doubles the power, right? The power to a power, you multiply. So you've got 2 powers going on where one of them is twice the other, right? Or maybe one of them is just 1 and the other is 2. Here, number 1, we've got a 1/2, x to the 1/2, and x to the 1st. X to the 1st is x to the 1/2 squared, because x to the 1/2, you might remember, means square root of x. That one actually could be solved as a square root equation. I'll show you 2 ways you can solve that. But it's also in what we call quadratic form. So all of these have kind of these 3 terms where one of them is a constant, and then the other 2 have powers of something where one of them is twice the other. One of the powers is twice the other. So what we're going to do is do what we call a U substitution. So let me go ahead and share my screen here and show you that. Okay, so I'm going to actually start with a fresh piece of paper, and we don't need a calculator. You might have noticed that it said no calculator. just turn this off here. Start with a blank document. And I'm going to make that full screen. Actually, I need to go back to tablet mode. There we go. So this is actually section 2.3, I believe. Equations in quadratic form. So you've got some number A times something squared plus some number B times something plus C equals 0. Number 1, x minus 5x to the 1/2 power plus 6 equals 0. So here, if you've emphasized that that's x to the first, you can see that x to the first is what you would get if you squared x to the 1/2. All right, square root squared is x, sure enough. So what we can do is we can substitute another letter, and we usually use the letter u for that middle term, x to the 1/2, because then u squared is going to be x to the 1/2 squared, or x. So then this whole equation can be written in terms of u and u squared. So we can replace x to the first with u squared and x to the 1/2 with u and get a quadratic equation. All right, the leading coefficient here was 1, so I didn't have to worry about that. That was like the A. And the B was -5, and the C was 6. So you do this substitution where you let u be the middle term, then you check to make sure that u squared is the first term. So now this should factor. These should all factor. So this should give you some practice with the factoring and using the zero product property. This should be u and u. The signs are going to be the same, but they're both going to be negative. So that means we want to find two numbers that multiply to give you 6 whose sum is 5. So that's 2 and 3. Sure enough, we get a -2u and a -3u. That gives you -5u in the middle. And -2 times -3 is +6. So then you set each factor equal to 0. U equals 2 or u equals 3. But then you have to go back to x. So then we use this original assignment of what we let u equal to go back to x. We let u equal x to the 1/2. So x to the 1/2 is 2, or x to the 1/2 is 3. And again, x to the 1/2 means square root. So how do we solve that? Well, we need to square both sides. And x is 4, right? If the square root of x is 3, then x is going to have to be 9. So these are the two solutions. Sort of makes sense? Let's do another one. Number 2. 2x to the 4th plus x squared, or 1x squared, -1 equals 0. Okay, so you want to notice again that if you let u be the middle guy, that u squared would be x to the 4th, right? So we're going to let u equal x squared so that u squared is x squared squared, which is x to the fourth. So we get an equation then in terms of u. 2u squared plus u minus 1 equals 0. And it should factor. This one, we've got 2u and u to get 2u squared. And then minus 1, we're going to have the signs different, but we're not sure which one goes where. So you just have to kind of try and see. This is 1u minus 2u. That's not what we want. So we want to switch those signs around. Right? We want this to be minus and this to be plus, so that we get a minus there and a plus there. Okay, so now we set each factor equal to 0. And solve for u. Adding 1 to both sides, 2 equals 1, divide by 2, u equals 1/2. And over here, subtract 1. Then go back to what did we assign? We let u equal x squared, right? It's always going to be that middle guy. So plug x squared back in for u. X squared is 1/2, and x squared is -1. So now we need to use the square root property, where you've got to remember could be positive, could be negative. Square root of 1/2, you take the square root of the top and the square root of the bottom. The square root of 1 is 1. And then we always like to rationalize denominators. So that's plus or minus √2 over 2. Those are 2 of your solutions. And then here, take plus or minus the square root of -1, which is plus or minus I. So this one actually has 4 solutions, which corresponds to the fact that it is a 4th degree polynomial equation, isn't it? Any questions on that one? All right, number 3. I need some more pages. Okay. Number 3. We've got some quantities in this one. X plus 1 squared minus 3 times x plus 1 equals 40. And there's more than one way to do some of these. I was going to show you another way to do this first one. Let's do this one first, and then I'll show you. So the u substitution way says, let's set this equal to 0, and notice that it looks kind of like a quadratic. But instead of just x squared, we have x plus 1 squared. And instead of just x in the middle, we have x plus 1. So let's just replace that with u, right? So then u squared is x plus 1 squared, and the equation becomes u squared minus 3u minus 40 equals 0. Just replacing the middle term, the middle parenthetical with u, and then that parenthetical squared with u squared. So then this should factor u and u minus 40, so the signs have to be different. So two numbers that multiply to give you 40 whose difference is 3. Can you type what you think those two numbers are in the chat? Eight and 5, you got it. And the bigger number needs to be negative to get minus 3 when you combine them, right? Minus 8u plus 5u gives you minus 3u. All right, so u then is either negative 5 or positive 8, right? Because if you set those factors equal to 0, you add the opposite and get the opposite. So then we go back to x. U is equal to x plus 1. So x plus 1 is negative 5 and x plus 1 is 8. And then that's easy to get x. You just subtract 1 from both sides. And get negative 6 and 7. Now, another option for this would have been to multiply everything out. To say, okay, x plus 1 squared, I can FOIL that. And then minus 3x plus 1, I could distribute the minus 3, right? Squaring out x plus 1, FOILing that gives you x squared plus x is plus 2x plus 1. And then if you subtract 3x and subtract 3, you get x squared minus x minus 2 equals 40. Yeah. And then setting it equal to 0, you get x squared minus x minus 42. And that factors two numbers that multiply to give you 42. Signs are different, so their difference would be 1. That'd be 6 and 7. So x equals negative 6 or x equals positive 7. So that works too. So sometimes there's more than one approach. Back with number 1, it was x minus 5 root x plus 6. Right? Another way would be to isolate the radical. You could say negative 5 times the square root of x equals negative x minus 6, and then square both sides to undo the radical. Then you get 25x equals, and you'd FOIL this out, and you would get a positive x squared, a positive 6x, another positive 6x, and a positive 36, because you got negatives times negative. And then if you set all that equal to 0, let's see, you've got a 12x minus 25x is minus 13x plus 36. And then factor that, minus 4 and minus 9. Gives you x equals 4 and x equals 9. All right, so there's a lot of times more than one way to do it. Not always, though. Number 2, the only thing that I maybe would do differently with number 2 is just realize that you could factor it in terms of x squared. You could factor this as 2x squared and x squared, and your plus 1 and minus 1, which one goes where? This one's plus. And then you could set this equal to 0 and set this equal to 0. 2x squared equals 1, x squared equals 1/2, and so then x is, you know, the square root of 1/2. And then here x squared equals -1, so x is plus or minus I. And you get that one. So you can actually factor a fourth degree like a quadratic. So this would be another approach. As opposed to using substitution. All right, let's look at number 4. Number 4, we've got 3 minus 10x to the -1 minus 8x to the -2 equals 0. So if we rearrange this, and actually I'm going to multiply by negative because I want that leading term to be positive. So I'm going to rearrange and multiply both sides by -1. So I'm going to get a positive 8x to the -2 plus 10x to the -1 minus 3 equals 0. Okay, now what I'm going to do is substitute u for x to the -1, because then u squared would be x to the -2. Okay, so maybe I'll over here I'll say let u equal x to the -1. Now what does x to the -1 mean? Reciprocal, right? 1 over x. So u squared being x to the -2 is 1 over x squared, right? Which is just the square of 1 over x. All right, but when we write this in terms of u, it just looks nicer. Factoring is going to be interesting because there's lots of options. To get 8u squared, I bet 4u squared and 2u squared is what we want. It could be 8u squared and 1u squared, but usually the numbers that are closer together work more often, just in my experience. So then for -3, all we can use is 3 and 1, one of them positive, one of them negative. So here's where you just want to kind of try. There is that AC method you can use as well. But trial and error works too if you just try things until you come up with something that works. That doesn't give you, oops, it's supposed to be just u, not u squared, sorry. This does not give us 10u in the middle, does it? So I'm going to switch the 3 and 1, switch the 3 and 1. So I'm going to put the 3 over here and the 1 here. And then I get a 12u and a minus 2u. That's more like it. That does give you 10u. So notice just switching the two numbers around changes it a lot when you have leading coefficients. The AC method, just to review that, if you prefer that, is where you take a times c, which would be 8 times -3, which is -24, and you break it back down into two numbers that add to give you 10, the middle number. So again, you have to use the fact that it's negative to have a plus and a minus. So plus 12 and minus 2 are the numbers that combine to give you a positive 10. So then what you do with those is you split up the middle term. You write it as 12u minus 2u. That's why those two numbers have to add up to give you that middle term. So then this factors by grouping. You can factor out 4u, and you're left with 2u plus 3. Here you can factor out -1, you're left with 2u plus 3. And so then you factor out 2u plus 3, and you're left with 4u minus 1. So either way, then when you solve for u, you get 4u equals 1 and 2u equals -3. Dividing by 4, u is 1/4. Dividing by 2, u is -3/2. So then you say, well, that's what 1 over x is. So what's x? I'm getting ahead of myself here. X is going to be the reciprocal, because reciprocating both sides of an equation is legitimate, right? 1 over x is 1 over 4, so x has to be 4. 1 over x is -3/2, so x is -2/3. All right, let me show you another way. The original equation was 3 minus 10x to the -1 minus 8x to the -2 equals 0, right? You could just write what that means. That's 10 over x, and that's 8 over x squared. And then clear the denominators. Because now what it is actually what we call a rational equation, where if you multiply both sides by the LCD, which would be x squared, you get 3x squared minus 10x minus 8, don't you? Because, oh, now my dean's calling me. Because multiplying both sides by x squared, you distribute, and one of the x's cancels here, right? Leaving you with 1, and the whole x squared cancels there, leaving you with nothing. And it's still equal to 0, because 0 times anything is still 0. So then, if you factor this, 3x and x, plus and minus, 4 and 2, or use the AC method. This doesn't work, so you switch around the 4 and 2. Oops. 2 and 4. So that's -12x. Yep, that works, because you want a minus 10x. So then, setting each factor equal to 0, you get 3x equals -2, x is -2/3, or x is 4. Same answers. But some of them, like I think this next one, yeah, number 5, the only way to go is substitution. Number 5 has x to the 2/3, which is cube root squared, and then plus x to the 1/3, which is cube root. And there's no way to isolate and undo both of those. So therefore, substitution is the only way. So we're going to let u equal the middle guy, x to the 1/3, which remember is the cube root of x. Because then this right here is u squared. Because x to the 1/3 squared, power to a power you multiply, 1/3 times 2 is 2/3. So you get just u squared plus u minus 6 equals 0. Nice, easy quadratic equation that factors. U and u, signs are different. Two numbers that multiply to give you 6, whose difference is 1, would be 3 and 2, and you want the bigger number to be positive to get a positive u in the middle, right? 3u minus 2u is positive u. And then set each factor equal to 0, you get u equal negative 3, and u equal positive 2. So now we go back to x. We look at what did we define u to be? The cube root of x. How do we undo a cube root? What's the inverse operation or inverse function from the cube root function? Cubing. Cube both sides. So then x is negative 27, or x is 8 are the solutions. Number 6 is even more robust. It has the same powers with quantities. So this one for sure you need substitution. So this one, you're going to let u equal that whole quantity to the 1/3 power. Okay, in other words, the cube root of 2x minus 1. Because then this is u squared. And the equation becomes u squared plus 2 times u minus 3 equals 0, doing that substitution. So just let u equal the cube root of 2x minus 1. Then we can solve this. Factor u and u. Let's see, two numbers that multiply to give you negative 3 and add to give you a positive 2 would be plus 3 and minus 1. So u equals negative 3, or u equals positive 1 when you set each of those equal to 0. So then you go back to x by substituting back the cube root of 2x minus 1 equals negative 3, and the cube root of 2x minus 1 equals 1. So now you've got to solve those two equations. Undoing the cube root, again, involves cubing. So 2x minus 1 equals negative 27, or 2x minus 1 equals 1. Add 1 to both sides. 2x equals negative 28. Divide by 2. X equals negative 14. Add 1 to both sides over here. 2x equals 2. Divide by 2. X equals 1. How are we doing on time? Oh, plenty. Number 7. Maybe I'll use a black pen. Number 7, we've got 4x to the 4th plus 11x squared equals 3. So first thing we got to do is set it equal to 0. And now if we let u be x squared, x to the 4th is u squared. maybe off to the side here, I'll write let u equal x squared to remind us how to go back. So we've got 4u squared plus 11u minus 3 equals 0. Let's see, factoring this one, should we use the AC method? A times C would be 4 times negative 3, which is negative 12. So to get 11, that would have to be a positive 12 and a negative 1. So if we split up that middle term, plus 12u minus 1u minus 3, we can factor out a 4u. We're left with u plus 3. And we can factor out a negative 1 and left with u plus 3. So the factors are 4u minus 1 and u plus 3. And you can check it here if you want. So 4u equals 1, or u equals negative 3 when you set them equal to 0. Dividing by 4, we get u equals 1/4. So what was u again? U was x squared. So x squared equals 1/4, or x squared equals negative 3. Take plus or minus the square root, don't forget. So plus or minus 1/2 are two of the solutions. And then over here, plus or minus the square root of 3i are the solutions. Again, 4 solutions for a 4th degree polynomial is typical. Don't forget that plus or minus. And also, this is one where, you know, I could have factored it directly up here as 4x squared and x squared and minus 1 and plus 3 if I wanted to keep it in terms of x, and then just set each of those equal to 0 and solve for x. You could get the answers as well. All right, that would give you 4x squared equals 1. So x squared is 1/4. So x is plus or minus 1/2. Or x squared equals negative 3. Oops, x squared gives you x equal plus or minus root 3i that way. So either way. Ooh, I'm getting hungry. It's hard having class right over lunchtime, isn't it? Number 8. X to the negative 2 minus 8x to the negative 1 equals negative 7. So one way to do it would be just to rewrite these, you know, as what that means, right? X to the negative 2 being 1 over x squared, x to the negative 1 being 1 over x, so 8x to the negative 1 being 8 over x, and then clearing the denominator by multiplying both sides by the LCD, which is x squared. Distributing, you get 1 minus, here one of the x's cancels, so you're still left with 8x equals negative 7x squared. So then add 7x squared to both sides and rearrange. And probably we'll get something factorable. Let's see. 7x and x. 1 and 1 both negative. Signs have to be the same because it's a plus 1 and got to be negative to get that 8. And sure enough, that works. Minus 1x minus 7x. So then you can set each factor equal to 0. X equals 1 is one solution, and x equals 1/7 is the other. Using substitution, you could replace x to the negative 2 with u squared and x to the negative 1 with u to the first. And you would get u squared minus 8u plus 7 equals 0 when you set it equal to 0. That would factor u and u, 7 and 1, both negative. So you'd get u equals 7 and u equal 1. But then that's what, x to the negative 1 is. And x to the negative 1 being 1 over x tells you to reciprocate. Right? So 1/7, and then 1 over 1 is just 1. So either way. All right, 2 more. This is my last page. Yep. Okay, so how about green? Number 9, x to the negative 4 plus 2x to the negative 2 minus 15 equals 0. So I'm going to let u equal x to the negative 2, which you want to remember is 1 over x squared, so that u squared is x to the negative 2 squared, which is x to the negative 4, or 1 over x to the 4. But it's really this one that you care about, right, for later. But when you do the replacement or do the substitution, you get u squared plus 2u minus 15 equals 0. So factor this one. 2 numbers that multiply to give you a negative 15 and combine to give you a positive 2. Signs have to be different to get a negative 15. So the 2 numbers difference has to be 2. So that's going to be 5 and 3. And you want the bigger number to be positive. And then setting each equal to 0, you get the opposites. And then we go back to x. So let's see. 1 over x squared is equal to negative 5. 1 over x squared is equal to 3. So that means we need to reciprocate and take plus or minus the square root of each number. So that's going to be plus or minus 1 over root 5I. Or if you rationalize the denominator, plus or minus root 5 over 5. Right? Because if you multiply top and bottom by root 5, you get the root 5 on the top and 5 on the bottom. And then here, x squared would be 1 over 3. So x is plus or minus the square root of 1 being 1, square root of 3. Rationalize the denominator. You get plus or minus root 3 over 3. Okay, one more. Oh, I need another page. One page. Number 10. The grand finale. X to the 2/5 minus x to the 1/5 equals 12. So first we want to set it equal to 0. And then this is going to be u squared, and this is going to be u. Right? The coefficients are just 1s. So u squared minus u minus 12 equals 0, where we have substituted u for x to the 1/5 power, which remember is the 5th root of x. So then this factors x and x, nope, u and u. Signs have to be different to give you a negative 12. So 4 and 3 have a difference of 1. You let the bigger number be negative, right? So that you get a negative u when you combine. So always double check though, when you're unfoiling, factoring, you want to guarantee that you get the first term and guarantee that you get the last term, and then always check your inside and outside and make sure that works out. Because if you don't factor it correctly, it's all wrong. So setting each factor equal to 0 gives you the opposites, -3 and +4. And then you go back to x. 5th root of x equals -3. 5th root of x equals 4. And how do we undo the 5th root of x? Raised to the 5th power. So that gives us x, and then -3 to the 5th is -243. And then 4 to the 5th is 1024. Nice. Any questions? Oh, question here. For number 6. Did I screw something up here? Let's see. Number 6. -27 plus 1. Oh, yes. Yes. Good catch. -27 plus 1. This is wrong. Thank you. That should be -26. Excellent. So -13. You got it. Any other questions or corrections? Anything anyone wants to see again? All right, so work on the homework, obviously, for 2-1 through 2-3. Try to, keep up. And then on Thursday, I'll send out an email, probably Wednesday night, letting you know, which recordings you should look at for Thursday's class. And just make sure you do those and do the homework for that. And then we'll hopefully be back together again next Tuesday. Fingers crossed. All right. Good luck getting the homework done, learning this stuff. You can do it. Ta-ta.